Hi everyone, welcome to my tutorial on nonlinear analysis of geotechnical structure using Salome-Meca 2017. In the first part of my tutorial, we discussed the various sources of nonlinearity and how they are handled in a finite element analysis. In this part, we will discuss the details of nonlinear solution techniques and also how those techniques are implemented in Salome-Meca or Code-Aster in brief. And in the next part, I will take up an example of using them in actual analysis. So here we go. So as I told you that the general strategy of nonlinear solution is basically we apply an incremental algorithm. We divide the load as function of some pseudo time. These are not actual dynamic load but static load. Still we express it as a function of time. Gradually the load evolves over time, and then we solve the nonlinear equation obtained by using well-known Newton's or Newton-raphson's method or some modified form of those methods. And in order to discuss the details, I will be using the training material published by EDF for that purpose. So we'll discuss the basis or basic of nonlinear analysis and how it is implemented in how it is used, not implemented, how it is used from the user's perspective in Salome-Meca or Code-Aster. I will not discuss the basic of the nonlinear finite element theory. Thorough details is not possible to be discussed. So I will discuss everything from a user's point of view, but I will try to give you the basic solution strategy first. So as I told you, to solve a nonlinear problem, we apply an incremental algorithm where the load evolves or load increases over time to its full value, and therefore the load is expressed as a function of some pseudo time. It is not the actual time because it is not a dynamic load, but it is used as a function of some time. And this expression as a function of time is necessary to apply the nonlinearity of the problem. And you remember that we have basically three types of nonlinearity. One is geometric, the other is material nonlinearity, and the nonlinearity due to boundary conditions. So since the boundary conditions may be applied, boundary deformations or boundary force, the applied force may be applied by some non-constant values. Therefore, we need to parameterize it or express it as function of time. Similarly, a nonlinear material, it produces a nonlinear stress strain curve, and therefore based on the deformation I need to find out the strain and the corresponding stresses from that nonlinear relationship, and therefore the precision of my solution will depend on those increment size. That is another reason why we need to express it as function of time. And the third reason is to reduce the nonlinearity of the problem, we need to cut it by smaller step size. That is shown in this next few slides. You see the boundary condition like prescribed force or prescribed displacement may not be constant. It may change with time like this. These are some examples of that. And in order to apply these kind of boundary conditions, we must express it as function of time. Secondly, a nonlinear problem, if we try to solve it in a single step, then my solution will be not accurate, Therefore, what we do, since any curve can be taken as made up of small segments of straight lines, therefore we can cut down it into various steps. Say this nonlinear load is provided in a number of steps, thereby reducing the nonlinearity in every step. So that is another reason why we need to take the load or deformation as function of time. Now, in solving a nonlinear problem, what is the basic strategy? Let us see that. We express everything as a function of that pseudo time t. Therefore, my deformations are functions of t, and also the external loads are functions of t, and the internal load as well are functions of t and functions of the deformation, of course, because it is a nonlinear material, and that deformation again is a function of time, as I told you. And due to equilibrium, at any time step t, my deformation must be such that the internal stresses or internal forces generated due to that deformation and the external force applied at that time instant, their difference must be 0 or very close to 0. Alright? Otherwise, equilibrium will not be achieved. So therefore, now in the time we discretize all the quantities in terms of the time step. I have time step 0, time step 1, like that. I may have a kth time step up to the end. And in the kth time step, I have the internal load L internal k, external load L external k, deformation uk, time tk, and stress strains, and of course the thermal parameter alpha, etc. And then I define the incremental quantity as the deformation at step k is the sum of the deformation at the previous step, that is uk minus 1, and the change in this deformation between these two time steps, which is delta u. So that's how we express it, as the deformation as an incremental quantity. Now, while solving a nonlinear problem, the basic of the Newton method, you all know that if I want to find 0 of this function, so xn I need to find out in nth interval, then what I do, I write the Taylor series expansion using the first order term only. So that is written as the functional value at the previous instant plus derivative of that function at that previous instant multiplied by the difference between the two instants. And in that case, the next solution at the next step, the solution giving me 0 will be obtained from this equation. This is famous Newton's or Newton-raphson method. And that is what is basically used in terms of finite element context in almost all the nonlinear solvers, including Code-Aster or Salome-Meca. The advantage of this method is that if I have a finite derivative of my function at those various instants, then the convergence is quite fast. If I find out the first trial value, first gauge solution sufficiently correctly, then the convergence is quadratic near the solution. So it converges quite fast. And of course the necessary condition is that I must have a finite value of this derivative. So this must not be equal to 0. This derivative must not be equal to 0. However, this computation of this derivative in finite element equations is of course quite expensive, and there are various ways to avoid that expensive process as far as possible. All right. Well, now while solving the nonlinear problem, we will apply Newton's method, and for finding the solution at any time step tk, I have to have many iterations, and those iterations are indicated in these equations by number n. Okay. So at any time step tk, my internal load is functions of u at the time step, and my external load is also function of that time step and that deformation, maybe if it is a boundary condition based load. And for equilibrium, this difference must be 0. The difference between internal and external load at any time step must be 0 or very close to 0 for a practical case. Now I can express the internal load in the nth iteration in one time step as a Taylor's series expansion. So the internal load at time step n, at iteration step n, is the internal load at its previous step plus derivative of that internal load with respect to the deformation at the previous step multiplied by the difference of the deformations between these two steps. So del un is un minus 1, the difference of the deformation in the current step and the previous step. Similarly, we will express external force in a very similar manner. Then if I take the difference, if I subtract one equation from the other, we get this equation. The difference from internal load at the previous step and external load at the previous step plus this derivative at the previous step multiplied by the incremental displacement must be 0, all right, for equilibrium. And therefore I can express this as the residual in the previous step, residual of the, that means the error in equilibrium. So difference between the internal and external load in the previous step, that is a residual or error. So that is expressed as the stiffness matrix at the previous step n minus 1 times the incremental deformation. And this matrix is called a tangent matrix. We will see the graphical meaning of it a little later. And this is defined as this operator. So derivative of the internal load at the previous iteration minus derivation of the external load at the previous iteration. And this is my equilibrium residual, error in equilibrium. And I will find a solution so that this error in equilibrium is nearly 0, or I will accept some very small value as a 0. Okay, that is what is the convergence criteria. So the global algorithm of solving the nonlinear problem becomes, we need to compute the internal and external forces, then compute the tangent matrix in the true Newtonian method, and solve that linear system, that is k times u equal to f. This is a force, nothing other than force. And after I solve that, I get the incremental displacement. So I add that increment of displacement with the previous displacement, thereby I update the displacement, and I evaluate the convergence, whether my residual is acceptably 0 or not. Now this computation of tangent matrix is quite expensive, therefore it is not computed every time, every iteration sometimes, and those methods are called modified or quasi-Newtonian methods. And of course, if I use the true Newtonian method also, even in that case we do not compute the tangent matrix exactly, but we compute at the Gauss points, okay, by using numerical quadrature. Now this is the graphical explanation of this Newton's method. So what I have is, I have a load step at time t0, which is f0, and I have the deformation u0, which is known at that time step, all right, and I have another force F star at another time step, maybe T star, and I need to move to the correct solution of the deformation at the next step. Excuse me. So this is where we paused. Now I have the force and deformation known at this time step, and I need to find the correct deformation at this load step. So what we do to reduce the nonlinearity, we divide it into two steps. So from f0 to f1 and f1 to f2. So my job is to find out the correct u1 at f1 and correct u2 at f2. Right? Now for that purpose, what we do, we first compute the tangent matrix at this previous time step, that is f0 or t0, and applying that time step, applying that tangent matrix and applying this force, I get the deformation, incremental deformation at this iteration. Okay, so k1n for nth iteration in the first time step is k1n, the tangent matrix, and by finding that I get this del un, all right, which is shown in this next slide. So my difference between the load is f1 minus f0, and this stiffness matrix into del n gives me this difference, all right, this difference. So by solving that, I find this del u1 in the nth iteration. Now using that, what I will do, I will update the deformation, and thereby I will get the u1 for the nth iteration. u1 for the nth iteration, which is u0 plus this del u1n, gives me the updated deformation u1n. All right. Now I will compute for this u1n, I will compute the internal forces, which is this much, and my external force is already there, and therefore I get this residual. Now whatever is this residual, I will compare with my acceptable value. If it is less than the acceptable value, acceptable error, then I will stop there. If it is not less than this acceptable limit, then what I will do, I will recompute a tangent matrix at this level now once again, and thereby I will get a new delta u1n, and from that, adding this to the previous iteration deformation, I will get a new deformation here. Okay, new deformation here. So I am gradually moving towards the true deformation in that manner. Is not it? So what I am doing is I am first computing the matrix, tangent matrix. Then I am solving the problem, solving the linear equations to get the incremental deformation. Then I have updated the deformation by adding this incremental deformation with the original deformation to get a new deformation, and then evaluate the convergence. If convergence has not been achieved, I will repeat the procedure. Okay. So again I will compute a new tangent matrix here. So that's how the nonlinear solution proceeds. All right. Now this matrix computation, in the true Newtonian method, we evaluate this tangent matrix at every Newtonian iteration for every time step. So what I do, my first iteration, I come here, I recompute the tangent matrix. In the second iteration, I come here, I recompute the tangent matrix. In the third iteration, maybe I am reaching the true solution. But since this computation of this tangent matrix is very expensive, therefore in quasi-Newton method, in modified Newtonian methods, we do not compute this new tangent matrix at every Newtonian step. Rather, we compute after certain iteration. So those type of controls are possible. So what we are doing is, say I am doing after say third iteration, I am recomputing the tangent matrix here. So first iteration, I have come here by using the same tangent matrix, same slope. I am coming in the second iteration to here and third iteration to here. Now I will compute a new tangent matrix, and then I'll come to the true solution more quickly. So that is how the Newton's method is modified, and those are called quasi-Newtonian methods. One such method is the Newton-Krylov method. There are other methods as well. So this is how we may avoid this costly tangent matrix computation. We may reduce. And another way to totally avoid the computation of tangent matrix in a given time step in every Newtonian iteration is just to use the elastic matrix. That is, the first tangent matrix will be used over and over again in the time step, and thereby I will gradually reduce the residual and finally achieve the correct solution. This is shown here. The same tangent matrix is being used, and thereby with large number of iterations I will be reaching the true solution. Now this method is useful when the system is very nonlinear, and when the tangent matrix, computed tangent matrix, becomes singular. If the matrix becomes singular, that means the derivative is not finite, it becomes almost zero, so I cannot apply the Taylor series approximation, and therefore I cannot get the next solution. So in those cases, we go for application of the initial tangent matrix, but the number of iterations are increased accordingly. That is another way to use the elastic matrix in modified Newtonian method. Okay. So why these quasi-Newtonian methods are needed? As I told you, since at every iteration computing the exact matrix is very costly, therefore we try to avoid it. And since we compute that matrix sparingly, therefore there are more iterations, but each iteration will be quicker. And thirdly, the elastic matrix achieve convergence for all generalized materials with lots of iterations, maybe thousands of iterations will be needed, but we are sure to get a convergent solution. You see, you know that a nonlinear solution may not converge in some situations. To get a converged solution, I can increase the number of iterations, but I can use the elastic matrix. Okay? And therefore, in the situations where the load path changes quite a bit, elastic matrix is a good choice, like in loading unloading cases in soil, say, because loading and unloading paths are totally different. They have different types of nonlinearities, and therefore elastic matrix is a better choice in such situations, right? And then for solving the system, we can use, in some methods we can use direct solver, in some other method we can use iterative solver. So those are method specific, and you can get those things in the appropriate documentation of Code-Aster or Salome-Meca. We'll discuss a little bit of that towards the end of this tutorial. And we can improve my solution, next solution, in any iteration by some methods like line search method or arc length method, etc. There are various methods to improve the solution by minimizing this functional called residual. I will not discuss the details of this, but those methods we can use for accelerating the solution process. And in order to evaluate the convergence, whether I have achieved a converged solution or not, I need to always find out the residual. And there are different types of convergence criteria available in almost all nonlinear finite element softwares. So also in Salome-Meca or Code-Aster. Here we have the absolute maximum residual, which is this absolute difference between the external load and internal load in any iteration, the maximum value, peak value of that in any iteration, and that must lie than the accepted amount of error must lie within that. It must be lesser or equal. That is one convergence criteria. Then there is relative convergence criteria, where I divide this absolute difference by the absolute value of the external load. That is called relative criterion, relative convergence criterion. So keywords are resi, globe, maxi, that means maximum global residual, and relative global residual, that is resi, globe, rela. Or if in some cases I can give some stress reference that you don't exceed the error by this much time of some reference stress, then it is called resi, refe, rela. So this is the equation applied for that, where the known reference load is known and some multiple of that I do not exceed. Okay, so these are various kinds of convergence criterion implemented in Salome-Meca or Code-Aster. Now, in order to use that nonlinear procedure in Code-Aster, what we can do is, one of the way is we can use experimental data for some materials like steel or metals, and that experimental data can be saved in a file, and that can be read, stress strain data can be read, and accordingly the nonlinear curve can be achieved, nonlinear solution can be proceeded. The operators used is this Liège function, that means read the function, available in the file unit 21C. This is an example, some file which has a logical unit 21, and the parameter, that means the independent variable there is strain, it is called FC. So this is a stress strain curve data which is read by the system, and it is stored as this F sigma. That means it is a stress data, and then we can define the material in terms of this stress data by this. So defi material, the initial Young modulus we can give, the Poisson's ratio we can give, and then the stress strain data is given under the keyword traction, and that traction is to be read from this function F sigma. Sigma is equal to F sigma, and then we can analyze. So this is also possible, but for soil it is not so useful, because you know that the stress strain curve of a soil depends on many factors like pore pressure, like confining pressure, like relative density, then type of soil. So we have to use appropriate constitutive relationships for soil. Those we'll discuss a little later. And then in order to have the actual nonlinear solution, the operator used is the stat non-line operator, stat nonlinear static solution, where I have to give the material, I have to give the type of behavior I want, and that is indicated by the keyword comportment. Comportment means behavior, and the relation is von Mises isotropic and this stress strain traction. So this is the keyword for using the experimental stress strain data, and the deformation is still small, petty. Okay, so we are not considering geometric nonlinearity here, we are considering only material nonlinearity. Now, as I told you that we need to express the load as some function of time, and for that we need to express it, the load we need to express as some function of time, and that function is called multiplier function, function multiplier, func mult, this is the keyword, so that at any time t, the load, which is a function of time and deformation, is given by the some multiplier function multiplied by the external load at t. Okay. Usually in case of static load like self load or live load, etc., it is we use a linearly increasing load. It is called a ramp function. So we can define the ramp function by the keyword defi function. That means define the function where the parameter is time, that is inst is for instant, parameter is instant, and the values are given. Value 0022 means at 0 the load is 0, at time 2 the load is 2. The value is 2, multiplier value is 2. And the load given is say 100 at the final time, so that at time 2 it becomes 200. Load becomes 100 multiplied by 2, this becomes 200. So this becomes my load along with the actual load applied and the multiplier function. So load is defined as a pressure load in this case, and in the nonlinear static analysis I use that load as the charge means load, and the multiplier function which is having a value of 0 at 0 and 2 at 2. So 2 multiplied by 100 will become 200 ultimately. So that's how func mult is needed to parameterize the load. All right. So this we have already seen probably. Now, in order to have the computation at different time step, I must give the system the list of times at which the system should give the solution to me, and that is done by these commands defi list real, that means define a list of real, and then using that list in the nonlinear analysis. So here what I have done is, you see here I want, these are my time steps. Time is varying from 0 to 1 to 2 at different steps. I can change this stepping at different regions of my time path, 0 to time. And here in this we are defining a list of real where w is 0, that means the starting value is 0, and interval is until 1, just qua means 1, until I reach 1 I should give 4 steps, so nombre is 4. So I have 4 number of steps to reach from 0 to 1, and then from then on onwards until 2, in order to reach from 1 to 2, here 3 steps are given, so nombre is 3, so it is shown here. I have 3 steps here. So I can increase the number of steps, I can decrease the number of steps by giving appropriate nombre parameter here at different regions. That is one way. There are various other ways that we will explore later on while solving the actual problem, maybe. So this is how we define a list of time, and then in the nonlinear static operator solver we supply this list of time as increment. Increment is the list inst, that means the time list, and this list inst is already defined here as L inst, list of time, and list of time defined is this one. So when I tell in the straight nonlinear operator stat nonline increment is this, then automatically it will follow these time steps. So this is how time steps are given to the system for the solution. So at every time step we will solve the system, and at every time step I will have to have number of iterations, Newtonian iterations or quasi-Newtonian iterations, whatever I decide to apply. Now one thing we should be careful is that this loading parameterized by multiplier function and the time definition must be consistent, otherwise there will be error. For example, here my func multiplier gave me the maximum time as 2, so my time list definition should also go up to 2 only, not beyond 2, so that at time instant 2 I get the actual load as 200 by giving the pressure load as 100 in this case. So those things must be consistent. We have to be careful about the time list definition and multiplier function. They must correspond to each other. That is important. Thirdly, there are some advanced controls possible. In order to have correct solution, we need to control the computation of tangent matrix, we need to control the time steps, etc. Because if I use smaller time step, my solution will be more easily convergent. So those things we can do in different ways. One way is, if I do not achieve convergence after some number of iterations, then I can ask the system to automatically reduce the time step. So time step cutting, that is called automatic cutting of the time step. So here we have given a time step for to start the procedure. If at any time step it does not achieve the correct solution, it does not converge, then what I can say is you check the event of error, that means the convergence is not achieved, and if it is so, then action is decoupe, that means you reduce the time step, cut down the time step. Okay. So in the list, definition of list, in this defi list inst command, earlier we used increment command, here we use defi list inst command to control this by automatic time step cutting, okay, in case of error. So these are some advanced controls. You see, in a nonlinear analysis you need precise tuning of the solution process, and that tuning depends on the problem at your hand. no general solution strategy can solve all the types of problems. That's why we need to play with all these parameters. We need to apply different methods and try again and again to have the converged solution. Then there is also a method of automatic step adaptation. There we don't give any time step. So from 0 to 2 there is only one step. I have defined the time list like that, and then we define in the defi list inst command, we ask the method as automatic. Thereby it will automatically create appropriate time step. Only thing we want to control is that those smallest time steps should not be less than 10 to the power minus 6. So pass mini we are saying as 10 to the power minus 6. And in most of the cases with such small time step, the converged solution is achieved. Okay. So when we apply these kind of controls, our solution is have more possibility of convergence, but the time taken will be obviously longer. The solution time will be longer. And then in order to apply the quasi-Newtonian method or appropriate Newtonian method, we have some other parameters like if I do not want to compute tangent matrix every time, but I want to compute only after 2 Newtonian iteration in any time step, then I can call that Newton, I can modify this Newton method by this react-iter. That means recompute after iteration 2. Okay, that's how I can remember it. I do not know the actual French meaning. Similarly, I can also ask the system to recompute matrix every third time step. Say, by default at every time step, recomputation of tangent matrix will take place. In one type step, I can stop recomputation at every Newtonian iteration by using this react-iter command. And also, if I want to control the computation time step wise, then I can use react increment operator. So here, if I use react increment, then at every, if it is 3, then every 3 time step, after every 3 time step, it will recompute the tangent matrix. And in the worst case of nonlinearity, we will go for elastic matrix. Then I will simply say that matrix is elastic. So that's how we can have the advanced control in the nonlinear solution process. And the default values in Code-Aster are this react increment is 1. That means at every time step it will recompute. React-iter is 0. That means at again every Newtonian iteration it will recompute, and the matrix by default is the tangent matrix. Okay. Then about the convergence criteria, these are my default values of convergence criteria. Iter globe maxi, that means in every Newtonian, every time step it will make 10 maximum iteration, Newtonian iteration. If we want to increase it, I can increase it. This is the default value. And the relative global residual is 10 to the power minus 6. These are my default values, but we can change it by these supplying these two operators. Okay. And but while changing it, while reducing the convergence acceptable value, we have to be careful that by reducing it, it may produce wrong results. You have to carefully look into the results whether they are physically meaningful or not if you change this. Okay. And secondly, if I supply only one parameter, then it will check only that parameter. If I give resi globe maxi as 10 to the power minus 5, it will not compute relative residual at all. And so if I give one of them, only that criteria will be given, checked. If you don't give anything, it will check only the relative criterion. But if you want to check both absolute residual and relative residual, then we should give the values of the both. Okay. And for maximum number of Newtonian iteration, in order to increase beyond 10, we can give iter globe maxi, maximum number of iteration in every time step. You can increase it to 20, 30, etc., depending on the problem at your hand. So these are some of the advanced controls we can achieve in Salome-Meca or Code-Aster in order to achieve a convergent solution. Now, before ending, I want to draw your attention towards the documentations available in Code-Aster or Salome-Meca. Unlike other free and open source softwares where it is relatively difficult to get good documentation answering all your questions, thanks to EDF, that the Code-Aster and Salome-Meca has a very extensive documentation. It is almost daunting, thousands of pages of documentation, and you can download all the full documentation for the appropriate version of Code-Aster from this web page. For offline reading even, you can download the zip archive, and then if you unzip it, you get an index HTML file. Once you load it, you get the all HTTP links from there for offline reading. And for static nonlinear analysis of geotechnical structures, these are some of the important documents we should be familiar with. This document is on thermo-hydromechanical modeling. If we want to analyze for pore pressure, along with pore pressure, effective stress, etc., or flow through the soil, seepage, etc., then we should know how to use those types of modeling, and the details are available in this document. These are document numbers. Then this is a must. You should go through this manual on stat non-line operator. Then this document gives us the various nonlinear material laws and how they can be applied in case of Salome-Meca solution. So this you can go through, at least the geotechnical materials. Then these are the reference manuals for Moore Coulomb failure law, and there is another CJS constitutive law made for soil materials, and this I think has some convergence benefit over the Moore Coulomb law, and therefore you can go through this manual as well. And we can find out the parameters for CJS constitutive law, CJS 1 for that matter. There are 4 types of CJS laws. The CJS 1, those parameters can be obtained from Moore Coulomb value, that is C, phi, and angle of dilation also. So these documents you should be familiar with at least while before solving the problem. And of course, this documentation, the English versions are machine translated, so they are not always very good to read. Sometimes they are even misleading. One example I can give you, say if you say auto, if you want to write auto, if you read the manual's English translation, you will get the command as car. They have translated auto as car, which is not acceptable. So we need to be careful while using those machine translated documents, but still the documents are very much useful, as my experience says, except some here and there some wrong translations are there. Of course, they are not very readable. The English language is not very good in all the cases. Very artificial kind of English is written. But still, without documentation, we will not be able to use the software appropriately. And so reading the documentations is a must, in fact. So I hope you enjoyed this tutorial. With this, we stop this part of the tutorial. We'll meet in the next part of the tutorial soon. Thank you.